earlier. And on the second page here, there's a link. This link will take you to the video lessons. So if you want to access the video lessons, you simply go to this second page and click on this link. This will take you to the video lessons. So I will upload this one today again.
Oh, we are only seeing the pi.
Pardon?
We are seeing the pi only.
Pi.
It is his network.
Not all.
Just leave the meeting and join again. Sometimes that helps. Have you been able to try that? I'll wait for maybe a minute or two. Is there anyone else who cannot see? Hello? Okay. So we can now start the class and try to mute your microphone. Mute your microphone. But if you have a question in the middle of the presentation, feel free to stop, put on your microphone and ask. So today we shall look at this group of integers modulo n. So we will start with a simple case. We consider the case when n is equal to 3. And then we'll try to explain that using this small case and generalize to the any other positive integer. So we set up the following. We have this set. We have 3 sets that we will set up. I think I will edit this slide so that they look better. This should have gone to the next line. I didn't notice this. But there's this first set, which I call 0 bar with a bar at the top. So it's a set of all multiples of 3. And then the second set here, which I call 1 bar, is a set of all integers that leave remainder 1 when divided by 3. And then the last one is a set 2 bar, which is a set of all integers which leave remainder 2 when divided by 3. Now here K, S, and Q are integers. So we can list the elements in these sets as below. So you can see this set 0 with a bar consists only of multiples of 3. And the set 1 bar consists only of integers which give remainder 1 when divided by 3. So that is integers that can be written as 3s plus 1, where s is an integer. The same for the last one. These are the integers which leave remainder 2 when divided by 3. So one thing you will notice is that all the integers, if you put all these sets together, it gives you back all the integers. You can see that by just counting. There are no gaps. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. You can see there are no integers being left. The other thing you can observe is that these sets do not have any elements in common, right? So they actually partition. This is a partition of a set of integers. They don't have anything in common. Okay, so let's move to the next part. I think this statement here just says what I've said. When you get the union of all the 3 sets, you get the integers, which is z, and any pair of any of these pairs are disjoint. Any pair of these sets are disjoint. They don't have this symbol here means the empty set. The intersection is empty. So this means the empty set. And the intersection of any pair is empty. So these are important facts. Just we need to keep track of them. Now, there's a line in the slide that is too low. But I'll just say what is on the line. This line simply says we pick three elements, U, V, and W. U is picked from this set, 0 bar. V is picked from this set, W bar, and 1 bar, and W is picked from the last set. So W is picked from this set. So we have three elements we are picking: U from this set, V from this set, and W from this set. So that line appears at the bottom here, but it's not very clear. So keep that in mind. That's why it's important for you to have your notebook as well. So we notice the following. If we add the elements U and V, because U is a multiple of 3, we can write it as 3k. V leaves remainder 1 when divided by 3, so we can write it as 3s plus 1. So when you add the two of them, we end up with another number which leaves remainder 1 when divided by 3. So this number will belong to this set, 1 bar. This new number that we get when we add U plus V. We can do the same for U plus W, and when we add U plus W, U is a multiple of 3. W leaves remainder 2 when divided by 3. So it can be written as 3s plus 2, where s is an integer. And this part here will simply be a multiple of 3. So I can write it as 3c plus 2. So when I add this, I still get another number in the set bar 2. So this bar, it does not mean average. Don't confuse it with the bar in statistics. It does not mean average. We do the same with V and W. Remember, V was picked from the integers that leave remainder 1 when divided by 3. So we can write it as 3k plus 1. W can be written as, maybe this should have been a different letter, so that it doesn't have to be the same letter as what we have here. But it's a multiple of 3 plus 2. And when you add these, you end up with a multiple of 3. So when you add two elements from this set, you get an element in this set, 0 bar. So an element from this 1 bar plus an element from 2 bar gives you an element from 0 bar. So it doesn't matter which elements you pick from the sets, they will all behave like this. So you can just choose to pick representative. Now, the next line simply shows what happens if you pick two elements from the same set. So if you pick two elements from the set 0 bar, when you add them, you will still get another multiple of 3. If you pick two elements from V is from 1, bar 1. So if you pick another element V prime from bar 1, if you add them, you get an element in bar 2, right? You'll get an element that leaves remainder 2 when divided by 3. So this gives you the addition of any pair of elements from any set and within a set, and the results that you will obtain. Are we together?
Yes.
Good. Now, since we are just doing addition, we can observe the following, that since all through we are just adding integers, we know that addition of integers is associative, so this associative property will be will be will be true. So this is true for this operation. Now, like we said, it doesn't matter which representative you pick from the set. These conditions will always be true. So we can just choose to pick 0, 1, and 2 as the representatives from each of the set, and then we can define addition on the set as follows. So if you add 0 plus 1, we get 1. So 0 is simply the set of all multiples of 3. Bar 1 is simply the set of all numbers that leave remainder 1 when divided by 3. So when you add anything from those two sets, you will still get bar 1 because you get a number which leaves remainder 1 when divided by 3. Same idea as here. So we get all the additions like this. So bar 2 plus bar 2 will give you remainder 1. We saw that here. If W is from bar 2 and we pick W prime from bar 2, if you add them, you will get something in bar 1. So we can define addition in that form for these sets. So you basically, you're adding the sets, but since it doesn't matter which representative you pick, you can fix your representatives to be 0, 1, and 2. So anytime you add, you're actually adding the sets, but you're picking a representative from the set to represent the whole set. Are we together? Yes. Hamuna swali hata moja. I can move on to the next slide.
Yes.
Good. So this it's actually, this set is called Z3, and we can actually set up a group table for it like this: bar 0, bar 1, bar 2 as the elements to be added, and then these are the results of the addition in here. So using the same ideas, we can set up 4 sets rather, so, and call it Z4. Here there is a type, there's an error. This should be Z3 subscript 3 here. I will correct that. So this set, which consists of these 0, 1, and 2, we call it Z3. I think we had defined it here. So it should be Z3. And we've seen that we can define addition on it, and this will happen. So this set will form a group under addition, where the elements are this bar 0, bar 1, and bar 2. And this is what we call the group of integers modulo n. And this addition is called addition modulo 3, because we are adding modulo 3. So using the same ideas, you can do it for Z4. Z4 will require 4 sets. So the first set will be bar 0, which are multiples of 4. And you have bar 1, which are all integers that leave remainder 1 when divided by 4. We keep going on like that until we reach bar 3, which is a set of all integers that leave remainder 3 when divided by 4. So if you list the elements of the set again, you will see this happening. Again, the sets are mutually disjoint and they partition the set of integers. So if you get the union of all these sets, you will get the integers again. And we can add the sets the same way we were adding the ones for Z3.
Hello.
Please mute your microphone. So just to test this, you can see if you add any element from here, 0 plus 1, you will always get an element here. Any 2 elements you add from bar 0 and bar 1 will always give you a number here. You can test that for all of them and you will see that it is true. For instance, if you get -4 plus -3 you will get what?
-7.
Maybe -3 should not be here. Or am I?
I think so.
Yeah,
It's
get -7, which is here. So if you add anything,
Okay.
0 plus 1, you will always get something here. If you add anything within bar 1 to itself, you will get something that is here. So for instance, if you add 1 plus 5, you get 6. 6 is here. If you add 9 plus 1, you'll get 10. 10 is here. So if you add anything within this set, you will always get something here. So we can think, using the same ideas, we can define addition on Z4 as follows. And we end up with this as our table. Again, this will form a group under addition modulo 4. So this gives us some 2 examples for 2 different values of n. And we should see how we can generalize and get some ideas. So the addition modulo 4, which we have just seen in a previous table, is simply defined as a plus b will be equal to the remainder when a plus b is divided by 4 for any elements a and b you pick from Z4. So if you go back to the table, you'll see what I mean. So you can see if you add, say, 1 plus 3 will give you 4. And the remainder when 4 is divided by 4 is 0. So 1 plus 3 becomes 0. You can try 3 plus 3 is 6. And the remainder when 6 is divided by 4 is 2. So that's how you get these elements in the table. Are we together?
Yes.
So this now describes how the addition is done, modulo 4. So anytime if you are working modulo 3, you will get the remainder when divided by 3, and so on. Now we can also define multiplication modulo 4. Under addition, Z4 will be a group. So we can conclude that. Now, the multiplication modulo 4 is defined as this. This is, you simply multiply the numbers and you get the remainder when this product is divided by 4. So that's what we call multiplication modulo 4. We shall illustrate this next. So in general, we define this set Zn to be equal to 0, 1, 2, up to n minus 1. So each of these sets will represent, so bar k in particular will represent a set of all integers that leave remainder k when divided by n. And we can define addition modulo n to be the result, the remainder when a plus b is divided by n. So a plus b here will be defined to be the remainder when a plus b is divided by n. So you just do the usual addition. After you do the addition, divide by n, and your answer is a remainder when you divide by n. So because for convenience, we can ignore these bars at the top and just write Zn as 0, 1, 2, n minus 1, up to n minus 1. So we have to stop at n minus 1 because the remainder when you divide by n cannot exceed n minus 1. The largest remainder you can get is n minus 1 when you're dividing by n. So Zn is a group under addition modulo n, and the identity element will be 0 because if you add 0 to any of the other elements, you still get the same element. We saw that with Z3 and Z4. So the identity 0, this set by 0 will act as the identity because when you add it to any other set, it doesn't change the set. But at this point, we just represent them as numbers because it doesn't matter which representative you pick from the set. So you just pick one number from the set to represent each set. So Zn is a group under addition modulo n. Clearly, if you add any two of them here, you will get another number. Using this definition of addition, you will get another number within the same set, so it's closed. We know that addition of integers is associative. So the second property of associativity will be satisfied. We already identified the identity element. The identity element is 0, because if you add 0 to any of these elements, you don't change it. And the inverse of k will be denoted by the negative of k. And that is just, since we know 0 is the identity, the inverse of k is simply the element which, when added to k, gives us 0, or gives us a multiple of n. So it's easy to find the inverse. So for instance, if we check in Z3, the inverse of 1, remember this operation here is addition. So the inverse will be denoted by the negative of an element. So the negative of bar 1 will be equal to 3 minus 1, which is 2. So if you add 1 plus 2, you will get 0. Right? The remainder when 1 plus 2 is divided by 3 is 0. So it means the inverse of 1 is 2, because when you add 2 to 1, you get the identity. So you may want to say the additive inverse, because the operation here is written additively. So because of this, we can write Z3 as 0, 1, and negative 1. Sometimes it's convenient to write it out like this. So 2 and negative 1 are essentially the same. We can see this. Let's go back and you will see why. Because earlier on I mentioned that it doesn't matter which representative you pick from the set. So if you, in the set that contains the integers that leave remainder 2, when divided by 3, you will see that negative 1 is one of the integers in that set. I think I will go back to the here it is. Here there is 2. Negative 1 is also in this set. So you can pick any representative in this set, it will still work. So instead of 2, for instance, I could easily pick 17 and it would still work. It will have exactly the same effect. I could pick negative 7, it would still work. So I can use any representative here, but it makes sense to use the smallest, but sometimes it is convenient to use negative 1 instead of 2.
Excuse me, sir.
Yes.
Sir, a number of us are waiting for you to let them in.
Where have they been? I gave them almost 20 minutes before the class started.
I don't know where they have been, but yes.
Okay, let's admit them. So now, like I said, please do not use the chat. I am not able to see the chat when I'm presenting. If there's something you need to say, simply put on your mic and you can interrupt me and speak. But if you can't speak, you can put it in the chat. But what you put in the chat, I cannot respond to immediately. It will have to wait. These latecomers are giving us trouble. I think I will stop admitting them now. There. So, like I said earlier, we now have I've been able to generalize this to the case where for any positive integer n. So I think I did not mention that n must be a positive integer. And we have illustrated that under addition modulo n, Zn is a group. We've shown that it's closed. We've been able to show that the closure is because if you restrict your remainders to 0 up to n minus 1, you can't get any other remainder when you divide by n. So you'll always get remainder as one of these numbers in here. That guarantees closure. We found the identity to be 0, and we've been able to figure out how to obtain the inverse of an element in Zn. So, and we know that addition of integers is associative, and therefore this will be a group under addition modulo n.
Excuse me, sir.
Yes.
Could you please repeat how to find the inverse?
Can you read here? You know, sometimes you should be able to read. The inverse of k is simply k is n minus k. So for instance, if n is 3, and k is 1, the inverse of 1 turns out to be 3 minus 1, right? Which is 2. So if I add 1 plus 2, I will get 0. 0 is the identity. So it means 2 is the inverse of 1. In the same way, 1 is also the inverse of 2. Is your question answered? But it's simple. It's really easy for you to get. You need to learn to pay attention and learn to read, because the definition is right here. If you pay attention and simply look at this, it should not be too hard for you to figure it out. So my suggestion is this: pull out your notebook and get your pen. Stop staring at the screen and write things down. You will not be able to learn very well by just staring, for mathematics especially. So have you pulled out your notebooks?
Yes.
Yeah, pull them out and write things down. When you write things down, they become clearer.
Excuse me, sir.
Yes.
Kindly take us to the definition of modulo 4.
I do what? Please repeat the question. Did anyone get the question?
Yes, you say that you could take us through the definition of modulo 4.
You want me to repeat the... I don't understand. You want me to repeat the section on
Definition.
addition?
Definition of modulo 4.
There is nothing like what we said is addition modulo 4 or multiplication modulo 4. So you need to ask a complex question. So what is it that you don't understand here? This will be more productive if you respond. So what is it you don't understand? We define the set Z4 as a set containing just these 4 elements. and we describe the elements here. We already saw how to add the elements using Z3, so I did not repeat that addition here. But we set up the table for addition modulo 4. So basically what you are doing here is when you add two numbers modulo 4, for instance, if you add 3 and 3, you will get 6, but you don't write 6, you write the remainder when 6 is divided by 4, and that is 2. Does that answer your question? So for each different value of n, you will have a different addition. So this, you will not think of Z3 as a subset of Z4. Z3 is its own set. Z4 is its own set. So the reason you don't think of Z3 as a subset of Z4, because look at what Z4 is. Z4 is made up of these, which look very different from the elements in Z3. Z3 is made up of these subsets of Z. So Z3 is not a subset of Z4. Cannot be thought of as a subset of Z4. So every value of n will give a different set and a different operation. In particular, we are talking about addition modulo n. We shall talk about multiplication shortly, but the focus now was on addition. Now, it's useful that you respond. You ask a question, then when it's answered, you need to tell me if you have understood or not. Who asked the question? Please let us know if you are okay so that we can move on. Mic is not working. Okay, so we'll just move on. If they have a question again, they will repeat it later. So I think up to this point, yes?
I was asking from the formula negative k equals to n minus k. So does this mean that modulo n is the same as modulo 0?
Modulo n is, n will be a multiple of n, so it fits under this set 0. Okay.
Okay, thank you.
Yeah, the remainder when n is divided by n is 0. So it will go into this set. Just follow the definition of the addition. Don't complicate anything. Okay, so we move on. Here we illustrate the concept of multiplication modulo n. Now we use the same elements from Z3 that we had earlier. U was from bar 0, I think V was from bar 1, and W was from bar 2, if I recall. It's repeated here. So if you multiply them, remember U was supposed to be a multiple of 3, and V should leave remainder 1 when divided by 1. And when you multiply them, when you multiply this, you will get a multiple of 3. So it means U and V will give you 0. You do the same for the others. If you multiply U and W, you will get 0. Anything, if you multiply 0 by any of the others, you get 0. Let's try multiplying V and W. So if you multiply V and W, you get 3s plus 1 multiplied by 3q plus 2. When you work this out, you still end up with an integer which gives you remainder 2 when divided by 3. You can obtain this by just expanding this. R you will find the value of R if you expand this. The same happens if you multiply V with itself, you get 1, but W with itself, you get 1 as well. So every element is its own inverse, if you like. And here you will see that V will act like the identity. Now, also multiplication of integers is associative, so that property will be inherited. So here is a multiplication for Z4 and Z3. So you notice how it's different. I have used this subscript here to indicate that this is multiplication modulo 3, but many times you shall just ignore the subscript and understand the type of multiplication from the context. So here I've also written multiplication modulo 4 to differentiate the two operations. So the idea is the same. Multiply the numbers and the result would be the remainder when the product is divided by 3. So for instance, if I multiply 3 by 3 modulo 4, I will get 9, but 9 gives me remainder 1. There must be an error here. Two times 3 should be 2. This should not be 1. This should be 2. Right? So make that correction. Because if you multiply 2 by 3, you get 6. 6 gives remainder 2 when you divide by 4. The rest I think are fine. And you can see it here because 3 times 2 gave you 2 here. It should be the same up here. 2 times 1 gives you remainder 2 when divided by 4 and so on. So I hope that makes sense. So we will notice that the identity element in both cases is 1. Now if you check Z3, 0 does not have an inverse because the identity element is 1 and there's no element which when multiplied by 0 will give us no, there's no unique element which when multiplied by 0 will give us 1, right? For Z3, 0 does not have an inverse. For Z4, 0 does not have an inverse. The same is true for 2. This is here by accident, so it should be a 2. That's why it appears like it has an inverse, but it doesn't have an inverse because this is an error. It should be 2. So 0 and 2 will not have an inverse for Z4. So that means both Z3 and Z4 will not be groups under multiplication modulo 4. So in general, Zn will not be a group under multiplication modulo n because 0 does not have an inverse. And there might be other elements depending on the value of n that don't have inverses. For instance, in Z4, we saw that 2 also will not have an inverse. But we just need to find one that does not have an inverse for us to disqualify it from being a group. But not all is lost because we can still create a group, a multiplicative group, by taking only the elements. So in Z3, only 1 and 2 have inverses. In Z4, only 1 and 3 have inverses. So you can create Z3 star, which is a multiplicative group, modulo 3, consisting of only 1 and 2, and Z4 star, which is a multiplicative group, modulo 4, again, which will consist of only 1 and 3. So this will give you the multiplicative groups, modulo 3 and modulo 4, respectively. You just pick the elements that have inverses, and you form the multiplicative group. So in general, as I mentioned earlier, 0 in Zn under multiplication modulo n, 0 will not have an inverse, and that makes it fail to be a group. But we can knock out all the elements that don't have inverses. Just pick the invertible elements and create a new set, which we call Zn star, and that new set now will form a multiplicative group. Now, the issue is how do you find the invertible elements? So if you want to find all the invertible elements in Zn, you simply find the elements that are co-prime to n, where the GCD of m and n is equal to 1. That means m will be invertible. We'll go back to the table to see this in a minute. So for those who did SMA 108, you recall that we say the following, that C is the inverse of A modulo n if AC is congruent to 1 modulo n. And this is true only if the greatest common divisor of A and n will be equal to 1. We proved this in SMA 108. So these will be the only elements that are invertible in Zn. So let's go back to Z3, our favorite examples. You can see 1 and 2 are co-prime to 3, so they will have inverses. And in particular, 2 is the inverse of 1 under this multiplication modulo 3. And 1 is the inverse of 2 as well. Again, here only 1 and 3 will have inverses. So the inverse of 1 is itself. Also, the inverse of 3 is itself, right? You can see that 3 times 3 gives you the identity. So 3 is its own inverse. 1 is identity itself. The identity is always its own inverse. So only those two will be, and you'll notice that 1 and 3 are relatively prime, or they're to 4. In other words, they leave the GCD with 4 is 1. So that's how you find the invertible elements, and those invertible elements are the ones that make up the multiplicative group, modulo n, which we call Zn star. So this is the Zn star. And we've seen this tells us how to determine if the invertible elements of Zn. Are we together? There are some people still trying to join. Can go back and admit them.
Excuse me, sir.
Yes.
I'm somehow confused. The universe of like under addition in SMA was it 205? You were told that under addition the universe of 1 is -1, but and the universe
So
of
the inverse of 1 under addition, when you're working with integers, this is a different set. You have to open your mind completely. This is not the set of integers. This is the set of integers modulo n. You can see the set of integers is infinite. Let me just go back to explain. You are working with a completely different set group. So get out of that group completely. Forget it. We are not working with Z here. We are working with Zn. Zn simply means, let's go back to the beginning. Zn consists of only n numbers, that is 0, 1 up to n minus 1. It's not the same as Z. It's a finite group. We have defined the elements of this. So the elements are not numbers, they're actually sets. And we define that here. So this is one element of Z4. It is a set. The reason we pick only one number to represent it is all of them behave the same way. So we just need one number to represent that set. All of them are multiples of 4. So there are only 4 elements in Z4. This is not the same as Z. Right? So we have seen that if you add any of these numbers to 0, it doesn't change. So 0 is our identity under addition modulo 4. Is that correct?
yes.
Yes. So you right now stop thinking of integers. Think of a set and a binary operation. So if the set happens to be integers and your binary operation is the usual addition, then your statement will be correct that the inverse of 1 is -1. But this is a different set. It's not the same set. I don't know if that makes sense now. Maybe there are other people with the same question, so you may have helped by asking. You have not responded. Have you understood?
Yeah, I'm okay with it.
Yeah, you're following now. So you
Excuse
really
me.
have to open up your mind. That's why I'm telling you this subject requires you to start reading early. Don't wait for the last minute. So if you went with that notion to the exam, you would not have passed. So you need to start reading early and capture all these concepts. They are new. Some of them will be new, so you need a lot of repetition for you to internalize them. So I hope that answers your question fully, or anyone else who had a similar question.
Excuse me, sir.
Yes.
So you said that. How about that one per
What about it?
with modulo 4? We have got negative 11 and negative 7 in that set.
What's wrong with negative 11?
So under if we divide that negative 11 by 4, how will the remainder be negative 1? Be 1.
You don't divide negative 11 by 4. The difference is 4. Can you watch at it?
Did you do SMA 108?
Yes, we did.
Yes.
Negative 11 divided by 4, the remainder is 1.
So it's also covered in SMA305.
Yeah.
Yes, please. Now, if this class has to be a joint effort, you must make an effort to revise your SMA 205, and some of these concepts are also in SMA 108. So I cannot teach both 205, 108, and 303 at the same time. It's going to, otherwise we will not move at all. So you must make an effort to revise your work. For your own sake, not for my sake. So if you just want to walk into class like a ninja, you will not understand anything. You have to put in the time and effort. There's no shortcut to this, please. So if you don't do that, you will waste a lot of our time in class asking things that you should already know. But this is simple. Look at this definition. Bar 1 says you're looking for all integers of this form. They leave remainder 1 when divided by 4. So can you find an integer, k? So for instance, if you multiply, if k is negative 3, 4 times minus 3 plus 1 will give me 11.
Yeah.
Is that correct?
Yes, it's correct.
Yeah.
So that's how you need to think. So it's all integers that are this form. But now for you to see that, all you have to do is to pay attention. That's why I'm saying, please take time and read and pay attention. We are looking for all integers of this form. So, and it doesn't matter what, here k is not restricted to positive integers. K is just an integer. It can
Understood
be negative.
now.
Huh?
Understood.
You're okay? Okay, but try to revise your 205. And then keep your mind really open. There are a lot of things here that will look different. So now you have confused me. I don't remember where I was.
We were under multiplication. Modulo 4. Multiplication of modulo 4.
I think we had passed this.
The Z.
At invertible.
So, yeah, I think. Was there any question on this? Hakuna swali? So one special case is when p is a prime, when n is a prime number, and let's call it p. Then zp star will just consist of all the non-zero integers in the set zp. So that's a special case. The example here is z3. 3 is a prime number. So Z3 star simply consists of all the non-zero integers in the set Z3. So we only remove 0 and we get Z3 star. That is because for a prime number is always co-prime to all other numbers that are less than it. All other integers, positive integers that are less than itself. So for when we have a prime number, ZP star just consists of all these elements. So if, for instance, if P is 5, the Z5 star will simply be 1, 2, 3, and 4. That is just a matter of definition. So I hope this makes sense now. Is there anybody with a question on Zn? So maybe what we need to remember here is that under addition, Zn, addition modulo n, Zn is a group. Under multiplication, Zn is not a group, but if we remove if we pick only the invertible elements to construct the set Zn star, then we have a multiplicative group. So under multiplication, it's not a group until you remove the elements which are not invertible. Under addition, it will always be a group, addition modulo n. Not the usual addition in integers, it's addition modulo n. Okay, so let's move on to something else. So here is a definition. A group G is said to be commutative, or sometimes abelian, if AB is equal to BA for any pair of elements in G. There should be a comma here. This is not a product. There should be a comma between A and B here. I will fix that before I share the slides. So if this doesn't happen, then G is said to be non-commutative. So if you can find just one pair of elements which don't commute, then we say the group is non-commutative. For it to be commutative, this must be true for all pairs. So if you just find one pair that does not commute, then it fails to be, the group fails to be commutative. So let's see, here are some examples. We know that the integers are a group under addition, real numbers, the complex numbers are a group under addition as well. And we have just discussed Zn, which is a group under addition modulo n. So this is not, this plus here is not the usual addition. So this plus is not the same as this one. This is addition modulo n. So you have to make that distinction. These are all examples of commutative groups because we know when we add two integers, we can add them in any order. So A plus B, for instance, will be the same as B plus A. So the general linear group of n by n matrices is not commutative because we know that matrix multiplication is not commutative. If you multiply two matrices, there is no guarantee that they will commute. There are some matrices that will commute, but not all of them will commute. So it failed to be commutative. The dihedral group of degree 3 or the symmetries of the equilateral triangle also will not commute. Also D4, the dihedral group of degree 4 or the symmetries of a square, those ones will not commute. You can check that they don't commute. If you will find some pairs of elements in those three groups that do not commute. Some may commute, but not all. And that makes them fail to be commutative, and we call them the non-commutative groups. Are we together?
Yes.
So what you can do is you can look at all the examples of groups that we have covered and try to classify them yourself as either commutative or non-commutative. If If you like, you can use abelian. Abelian means the same thing as commutative. So here is a theorem. It says let G be a group with identity element E. So suppose we have two elements, E prime and E double prime. Again, this has nothing to do with the calculus. We're just using this to differentiate the two elements. Suppose we have two elements. We label one E prime and the second one E double prime in G. And it turns out that E prime G is equal to G for all G in G. Then we must conclude that E prime is the same as the identity element. In other words, if anything behaves like the identity element, it must be equal to the identity element. So that is on the left. The same is true for this. If you have something that behaves like the identity element on the right, then it must be equal to the identity element. So it's unique. The identity element is unique. Any other element that behaves like the identity has no choice but to be equal to the identity. We shall prove this in a minute. So essentially what that part says is that the identity element in a group is unique. You can only have one element, one identity element in a group, not more than one. So the next statement says, suppose we have two elements in the group, H prime and H double prime. And we can find another element, let's call it G, such that H prime G is equal to E, right? So this is not for all G, it's just for a fixed element in G. We find that H prime G is equal to E. Then it means this H prime must be the inverse of G. So anything that behaves like the inverse must be equal to the inverse. That is on the left. The same is true if anything behaves like the inverse on the right. So this GH double prime is equal to E. Then it must be equal to the inverse. Does that make sense? So the last statement of the theorem is that the inverse of G just gives you G. So let's prove this. I think there's some people trying to join. We can let them in, then we continue. So so the proof, let's prove the first one. It's important to recall the theorem before we do the proof. So here the first thing we are assuming that we have an element E prime, which behaves like the identity on the left side. So we need to show that this element must be equal to the identity element itself. And the reason we can say that once you mention that this is a group, automatically it must have an identity. So that is automatic by definition of a group. So let's take the assumption in the theorem. It says that E prime G is equal to G. Now we know that E prime is the same as E prime multiplied by the identity. So it happens that E prime is just an element from the group. If you multiply it by the identity in the group, it won't change. It will be, so we can multiply it by the identity. Now the identity in the group can be written as a product of G and its inverse. So I can replace the identity with G inverse. And I can use the fact that the operation of a group is usually associative. So I can put my brackets anywhere. Now, already I have made this assumption that E prime G is equal to G. So I can replace E prime G with G, or I have G inverse. And by definition, if I multiply any element in the group by its inverse, I will get the identity. So we have shown that this E prime, which behaves like the identity, so we have used that bit where it behaves like the identity here. If that happens, then this E prime is exactly the same as the identity element. So the same ideas are used for an element that behaves like the identity on the right. So if E double prime E double prime behaves like the identity on the right, then we show again that it's equal to the identity element. So here we write E double prime is equal to E double prime. Again, the identity can be replaced by G inverse G. So the order in which we write this product is so that it can be useful to us at the next step, because this can also be replaced by G inverse, but G inverse will not be useful to us at the next step. So our preferred order is G inverse G. Then we can put our brackets anywhere. And we've already made the assumption that GE double prime is equal to G, so I can replace this with G. And therefore, G inverse G will be equal to the identity element. Again, here we have shown that if anything behaves like the identity on the right side, then it has no choice but to be equal to the identity. So this confirms that you can only have one identity element in a group. You can't have more than one. So that's the statement. Now the second part was to check if anything behaves like the inverse, then it must be equal to the inverse. So here H prime G behaves like the inverse of G, but on the left. That's the assumption we make. Suppose this is true, then we need to show that this H prime must be equal to the inverse of G. Now we know that H prime is the same as H prime multiplied by the identity. Anything multiplied by the identity in the group is left intact. So this is just the same as H prime. There's a prime missing here. We have to correct this. Anyway, I can replace E with G inverse. Then I have H prime G here, but I know that H prime G is E. So I'm left with EG inverse, and that is just G inverse. So I have shown that H prime is equal to the inverse of G. It was behaving like the inverse here, and we have shown that it must therefore be equal to the inverse. The same happens if you consider an element that behaves like the inverse on the right. We end up showing that H double prime is equal to the inverse as well. Again, here we simply multiply by the identity on the right to have H double prime is the same as E H double prime. We replace the identity by G inverse G. We use the associative property to shift our brackets here. You can shift the brackets anywhere you want for the group operation. Again, use the assumption that GH double prime was E. We replace this with E. Then we have G inverse E is just G inverse. Again, anything that behaves like the inverse on the left side must be equal to the inverse. So again, this simply tells you that the inverse of any element is unique. An element in a group cannot have two inverses. There's only one inverse. So an element in a group cannot have two inverses. That's what this tells us. So the inverse of an element in a group is unique. Remember what I told you last time? When you're talking about the inverse, you must talk about the inverse of an element in the group, not the inverse of the group. The group itself does not have an inverse. It's each element that has its own inverse. And different elements will have different inverses. So this statement again simply says that an element in a group can have only one inverse, no, not more, exactly one inverse. The last statement was to check that the inverse of G is equal to G. So the way to check that is as follows. If I'm told that this thing is the inverse of this one, how I check that is just by multiplying them. And if I multiply them, I should get the identity. Anything I multiply by G inverse to get the identity must be its inverse, right? So if I multiply G by G inverse, by definition, this should give me the identity. So it means the inverse of this element, G inverse, is just G. Because that's what you multiply by G inverse to get the identity. This follows from the previous theorem, which says anything that behaves like the inverse must be the inverse. So G here behaves like the inverse of G, so it must be the inverse, like the inverse of G inverse. So it must be the inverse of G inverse. So again, the inverse of G will be equal to G. That's what this last one says. Any questions on this? Is there any question? Are there some people still trying to join? I think they have been allowed in now. Can you still hear me?
Yes.
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 Yeah. So you need to find time again and go through this carefully.
Yes.
Yes. So it's unlikely that you will understand this the first time you look at it. So it's necessary. It's mandatory actually that you go back and read this again over and over so that you internalize the concepts. But the video will be available if to be watched later. So let's look at an example here. The example says, let G be a group, and we need to prove that the inverse of the product of A and B is equal to the product of B inverse and A inverse in that order. So you reverse the order of B and A, B inverse and A inverse. So if I want the product of AB, it's the same as B inverse, A inverse. So let's solve this. Our target is to show, because what have we been told? We've been told that this element here, B inverse, A inverse, is the inverse of AB. So if I want to confirm that, the only thing I need to do is to multiply them. I multiply AB with this element, and if I get the identity, then I will have confirmed that this element here, this product, B inverse, A inverse, is a inverse of the product, AB. Are we together up to that point?
Yes.
That is a strategy now. So let's implement the strategy. So let's multiply. That's all we need to do. Multiply AB with B inverse and A inverse. Again, use the associative property of the group operation, so which means you can put your brackets anywhere. So we group B and B inverse to get the identity, and when we can drop the identity here to get A inverse, because the identity has no effect, leave the product intact, and if you multiply A by A inverse, you will get the identity. So what has happened? I have multiplied AB, this product AB, by this product B inverse, A inverse, and I have gotten the identity. So what does that tell me?
Yes.
Okay. Now it's making sense. So it's telling me that this thing must be the inverse of AB. because when I multiply it by AB, I get the identity. Again, this follows from the assumption that the inverse in a group is unique. So if you find anything that behaves like the inverse, it must be the inverse. So we make that conclusion that the inverse of AB is equal to B inverse A inverse. So if the group is commutative, then you can switch this. But if the group is not commutative, you can't switch these two. You will have a totally different meaning. So are we together?
Yes, yes.
Good. So we look at another theorem. It says let G be a group and let A, B, X, Y be an element of G. The elements are G. Pick 4 elements of G. Then the following will be true. If AX is equal to AY, then X
Excuse
must be
me.
equal to Y. Yes.
The last slide, please get back to the last slide, the previous slide. I have a question. So the AB times B inverse A inverse, should we have the 2 brackets or should we have one? Because if you have the 4, I guess it should expand. Yeah, I don't know.
I don't understand what you say.
Multiplication is not addition or subtraction.
So is it which brackets? This
Yeah,
one?
no, the previous one. Hapa
This
nyuma,
one?
yeah, those. Yeah, should we expand ama we just commute zikiwa na ziko 4 instead of 2? So
We are not commuting. We are just, remember, the group operation is associative. So you can put these brackets anywhere you want. So I can, instead of having them around A and B, I can put them around B and B inverse. It will still be fine.
so you haven't multiplied.
I don't understand. What multiplying do you want me to do?
Like-
when you put the brackets here,
Hello.
then you multiply B and B inverse. You get the identity. So for instance, if you are multiplying, say, 2 times 3, and then you're multiplying again by 4 times 5, you can multiply the 3 and 4 in the middle first, right?
Yeah.
After you multiply the 3 and 4 in the middle, then you can multiply with the rest. That's what I'm doing. Although it's not the
Okay.
same as for numbers, but
Yeah.
the idea is the same.
Oh, okay, thank you.
So there's nothing to expand here. So I don't understand what you mean by expanding.
Okay, good. Thank you. I've gotten.
So the theorem here says if you have these 4 elements, A, B, X, and Y from G, then this will be true. If AX is equal to AY, then X must be equal to Y. So this is called the left cancellation law. That means you can do away with the A on the left on both sides. The next one says if XB is equal to YB, then X must be equal to Y. So this is the right cancellation law. So in other words, if you multiply by the same thing on the right, you can also, it simply means XB is equal to YB simply means that X must be equal to Y. So let's prove this. So let's prove the first one. The first one assumes that AX is equal to AY. We can pre-multiply both sides of the equation by A inverse. So if you multiply both sides of the equation by A inverse, we can shift our brackets so that we have A inverse multiplied by A to give us E. The same on this side, A inverse and A will give us the identity, E. And then we can drop the identity because the identity leaves the element in gives us x is equal to y. So that proves the left cancellation law. So you will notice that the cancellation here involves multiplication by the inverse. It's not the cancellation that you normally do when working with real numbers, where you just cross this out and cross this out. Here your cancellation involves multiplying by an inverse. The reason you cannot cancel out is that the elements you're dealing with are not numbers. They can even be matrices, so you can't just cancel them out. You have to use the inverse to cancel them out. So the next thing is says xb is equal to yb. Again, the same idea. You post multiply both sides of the equation by the inverse of b, and you end up with xe is equal to ye, where e is the identity. And of course, the identity leaves each element intact, so we can conclude that x is equal to y. So this the left cancellation law and the right cancellation law. They are both cancellation laws for groups. So now the impact of this is the following. If you work out a group table, each element will appear exactly once in a row and exactly once in a column. And you're not counting the headers. The headers are not counted. The header row and column, you don't consider them. Let's see if we can illustrate this using one of the previous examples. So, too fast. So for instance, if you look at the multiplication table for the symmetries of an equilateral triangle, so you don't consider this header, the header, column, and row. What you need is only these ones, and you will notice that there is no element that will appear twice here, and there's no element that will appear twice along that row. That is true for all the others. If you start from here going forward, there's no element that will appear twice. If it appears twice, then that will not be a group. If it's a group, then it must appear exactly once. So those are that's the implication of the cancellation laws for a group table. So it can help you to tell whether you are doing your application correctly. If you see that if you know that it's a group and you filling up the table and you see that an element appears more than once along the row, then it means you're doing your multiplication wrong. As long as it is a group, that will always be true. If it's not a group, that may not be true, but if it's a group, that's guaranteed. So are we together up to that point?
Yes, sir.
That would be a good place to stop. So tomorrow we can start on this new topic, the homomorphisms. Is that okay?
Yes.
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 Or maybe you still have the energy. You can continue.
Perhaps not.
Yeah.
No.
Not really.
Let us prepare for the next class at 10.
But which preparation? You just switch on. Join.
We relax a bit. Let us prepare for the next class at 10.
We have
And
another
we take
class at 10.
breakfast.
And we take breakfast.
Kunywa chai kidogo.
Yes. We relax a bit.
And take breakfast.
Okay, that is fine. You can let me stop the recording.
Okay, nice day.
Where can we get this recording?
Um,
Mute.
But
I will just share
YouTube.
my screen again.
Link.
Can you see my screen?
Yes, we can.
Yes.
Yes.
So now I told you at the beginning of the class. That's why it's really important to pay attention. You see, there is this first page of the slides. I shared this last time.
Yes.
I think most of you should have it by now. So you, after the title page, there is a page which has a statement here that says watch the video lessons. Click here. So if you click on this, it will take you to the channel which has the videos.
Okay.
Is that okay?
Yes.
Yeah.
Fine.
It's okay.
Yeah.
Yes.
Yeah, so there is that, but I also shared the link to the channel much earlier in the WhatsApp group. I don't know if Eugene is around. Eugene and Paul. Who is the one? Is Ndegwa also here? Ndegwa from the computer group.
Okay, they shared in the WhatsApp group. We received them.
Yes, but are there some people who are not in the WhatsApp group?
Yes. That's why Katulul.
Wenye anatumia kadida.
Are you
I'm
connecting to
also
the
setting up the
videos?
SOMAs. I'm also setting up the SOMAs for this group, the SOMAs group. So I will, I think you will be able to access it. I don't know how the automation how far it has gone, but they were supposed to automate so that once you register, you're able to access the class. On Thomas. So I will put up the link there as well once
Okay.
once it is set up. But I have shown you where to get it. Once you get this set of slides, there's a link in the slides. You just click on it and go to the. And the class rep also has a link to the channel. And he has said the people downloaded. So any other questions?
No questions.